So in today's class, we'll discuss what happens when optical pulses are traveling through nonlinear media. Right. So far, basically, all of our discussion has been with monochromatic waves. So we have different laser beams, let's say at different frequencies, which are interacting in a chi3 medium, right? But all of those fields are at a single frequency. But a lot of nonlinear optics work is done with pulsed lasers, right? Where the optical power is a function of time, right? So, and by Fourier transforms, we know that any finite duration pulse in time will have a frequency spectrum which is continuous, right? So it will have a continuous band of frequencies. So if such a field is propagating or interacting in a nonlinear medium, specifically a chi3 Kerr medium, then how do we analyze such a case, right? So that's what we'll look at today. So topic is pulse propagation. In Kerr nonlinear medium. Right, so let's first look at what we mean by optical pulses, right? So what we mean is that, so the intensity or equivalently the power as a function of time has some finite duration. Right? So a monochromatic field, you know, would be a CW field where the intensity will be constant with time. Right? But for pulse, you'll have some peak with some pulse width, right? And so basically, when such a pulse propagates through a medium, let's say which has chi3 nonlinearity, then so we'll see basically how we analyze such a case, right? And specifically, we'll also see that the dispersion of the medium becomes important. So specifically, let's say this beta 2, which is the GVD parameter, right? So for pulses especially, that becomes very important because we have many different frequencies traveling together, right? So the dispersion properties of the medium will also become very important. So right, so this medium will be characterized by some dispersion properties and some nonlinear properties. So chi3 or equivalently the nonlinear refractive index N2 or equivalently this effective nonlinearity gamma. Right. So if you have a pulse like this in time, right? So let's say the pulse duration is tau p. Right. So there are various ways to define the pulse width, but let's say we define it by the half intensity level, right? So full width at half max of this pulse in the time domain is tau p. That's the pulse width in time. Right. So if you take the Fourier transform and look at the frequency space, so as a function of frequency nu, if you plot again the power as a function of frequency nu, then you'll again get some continuous distribution, right, which has some bandwidth built in, right? So this delta nu, the bandwidth in frequency space, is related to the pulse width in time, right? And you know that they are inversely related, right? So this delta nu, again, if we define delta nu as some sort of full width at half max, so if this is 1 and this is 0.5, right? Then the bandwidth is related to inversely related to the temporal width, and you have some constant A here, which depends on the particular shape of the pulse, right? So, for example, The most common type of pulse is a Gaussian pulse, when this is a Gaussian function, right? So for example, this will be some e to the minus t square by tau square, right? So for a Gaussian pulse, this A is 0.44. But you could have other shapes for pulses, right? So for example, another kind of common shape is a secant hyperbolic. So 1 over cos hyperbolic, right? So the pulse would be secant hyperbolic of t over tau, right? So for such a pulse, A is 0.36. But anyway, so that's just a constant which depends on the shape of the pulse. But in general, of course, the bandwidth is inversely related to the pulse width. So if you have a narrower pulse in time, you have a wider frequency spectrum. Of course, the ultimate limit of that is when you have a CW pulse, so infinite extent in time, and you have a single frequency spectrum. Right? So many times this spectrum is also denoted in the, instead of the frequency space, we denote it in the wavelength space. So so basically the spectrum you can either plot it in frequency or wavelength, right? So in wavelength also it will look something like this, and it will have a bandwidth delta lambda, right? And delta lambda is related to, of course, delta nu, right? So we know the relation between lambda and nu. So nu is c over lambda, right? So that means delta nu or the magnitude is c over lambda squared delta lambda. Right? So you just differentiate both sides. So the d nu or delta nu is related to d lambda or the width in lambda by this factor c over lambda squared, right? Where lambda, so specifically this will be some lambda naught square, where lambda naught is the center wavelength, which is c over nu naught, where nu naught is the center frequency, right? And that center frequency will be defined by the sort of the carrier wave, right? So this is the intensity profile. But if you look at the electric field, of course, it's oscillating at a frequency which is very high, right? So that's so this oscillation is given by some e to the I omega naught t, right? So this omega naught is basically this nu naught center frequency, right? And then c over that is. Right, so give you some sense of numbers. So if this pulse width in time, tau p, is let's say 100 femtoseconds, right? So 10 to the minus 13 seconds, which is sort of typical of a pulse laser, ultra short pulse laser. Then for a Gaussian pulse, the bandwidth you can calculate is about 4.4 terahertz. Okay, so 4.4 times 10 to the 12 hertz is the bandwidth for a 100 femtosecond pulse. And if you calculate in terms of wavelength, of course we need a center wavelength, right? So let's say the center wavelength is 800 nanometers, which is again like typical of pulse lasers. So then delta lambda, you can see, will come out to be about 9 nanometers. Okay. So those are sort of the typical numbers. Okay. So bandwidths of a few nanometers in wavelength or in frequency, few terahertz. Of course, you can also have much shorter pulses, in which case you can have much wider bandwidths. or equivalently longer pulses and shorter vibrate. But those are some typical numbers. Okay, so first we can just see qualitatively what will happen, right? So if you have a pulse like this traveling through a medium which has both nonlinearity, specifically Kerr nonlinearity, and dispersion, what will happen? So we can look at each case, right? So what will happen due to dispersion? Basically, you have a bunch of frequencies present in the pulse, right? And dispersion is basically telling you that the different frequencies are traveling at different speeds, right? So especially beta 2 means group velocity dispersion, which means the group velocity depends on frequency, right? So different parts, frequency components of the pulse are traveling at different speeds, which means like after traveling through the medium, the different frequency components arrive at different times, right? So that leads to a broadening in the pulse, right? That would lead to a broadening in the pulse. But so due to beta 2, in the time domain, what should happen is that the pulse should, if this is the input pulse, then my output pulse should broaden in time, right? And that's just because different frequencies, some frequencies arrive earlier, some frequencies arrive late, right? But in the frequency domain, nothing should happen, right? So due to dispersion, the frequency components which were present at the input are the same which are present at the output. Nothing happens to the spectrum. Only the relative phases of the different frequencies change because they travel at different speeds, right? So which leads to broadening in the time domain, but in the spectral domain, nothing happens. Right? Now, if we look at, let's try to imagine what will happen for medium which has nonlinearity, right? So we know that when a field propagates through a Kerr nonlinear medium, it can experience what is called self-phase modulation, right? So depending on its own intensity, it modifies its own phase, right? So then it acquires a nonlinear phase phi, which we can or we know is proportional to the intensity, right? So for monochromatic beams which we've been dealing so far, the intensity is constant, not a function of time. So this we didn't have this t, right? Right. So we had something like n2i here or gamma p. But now, since intensity is a function of time, this nonlinear phase shift is also a function of time, right? Assuming, let's say, the response of the medium instantaneous compared to the pulse width. So basically, at each time, the material responds instantaneously, and whatever is the intensity at that particular time, it gives a nonlinear phase shift. So now we have a time-dependent phase shift on the pulse, right? And a time-dependent phase we know is frequency, right? So basically, we introduce new frequencies again, which are time-dependent, right? This is called a chirp when the frequency, the instantaneous frequency in a pulse becomes dependent on time. That's called a chirp, right? And basically, that's given by the derivative of the nonlinear phase. So basically, we are introducing new frequencies because this phase is now time-dependent. So depending on the pulse shape and the intensity, we'll introduce new frequencies. So basically, if you look at the spectrum, so if you have some input spectrum, then you could get broadening in the spectrum because of the introduction of these new frequencies, right? Due to self-phase modulation. Whereas in the time domain, this self-phase modulation does nothing, right? So in the time domain, the pulse remains the same, right? Because it's only reducing a phase, so the intensity as a function of time remains the same, right? So you can see the two aspects of the medium sort of introduce complementary effects, right? So dispersion doesn't change the spectrum, but introduces broadening in the time domain, whereas the Kerr nonlinearity doesn't do anything in the time domain, but introduces broadening in the frequency domain, right? So I hope qualitatively that's clear, right? Of course, we'll go through the math and see how it exactly, and quantitatively see how these things happen. Okay, so to mathematically analyze these things, first we need basically a pulse propagation equation, right? So, for example, like we have these canonical propagation equations for analyzing monochromatic waves, right? We start from that and then we get some coupled amplitude equations between the different waves. Similarly, we need some equation for pulse propagation in a nonlinear. Okay. Right. So our starting point is, of course, the wave equation. Right. So we start with the 1D wave equation. So let's say the direction of propagation is z. Right. And so we have some optical pulse, which is traveling through, let's say, a fiber or a waveguide, and the direction of propagation is z. So we can write down the wave equation, right? So the starting point is the same that we had even for monochromatic waves, right? And how we derive the canonical propagation equation. So we start with the wave equation, and recall that for a dielectric medium, basically on the right hand side we had this polarization of the medium acting as a source for the wave, right? And so recall we had this polarization as a linear and nonlinear part, right? The linear part will just give me some refractive index, but the nonlinear part will give me wave mixing, etc. Okay? So we'll do something similar here. Right, and then this electric field is now a function of both position and time, right? So there's a time within the pulse, and then of course it's propagating along z, so it's a function of position. So we write it as an amplitude Az of t, and take out the fast varying carrier wave component separately. We write beta naught z minus omega naught t. Right, so omega naught is the carrier frequency again. So if I look at the electric field profile, if I plot, so at some particular z, if I plot E of t versus t, it looks something like this. Right, where this envelope, right, this envelope is basically a at the position z, a of t, right, and this the oscillations at the carrier frequencies, this e to the I omega naught t, that's these oscillations here. So the frequency of these oscillations are the carrier frequency omega naught, right? So that's given by the wavelength, right? So omega naught is 2 pi c over the central wavelength of my source. Right. So typical wavelengths, like in few hundred nanometers or microns, this frequency will be hundreds of terahertz, right? So these oscillations will be very fast, and then this envelope will be of the order of, as I said, so typical cycle times here. So if you look at the time period of the cycle, right, which is 1 over omega nu naught, right? That's the time period of this oscillation cycle. That's typically a few femtoseconds for wavelength, let's say near 1 micron, right? So let's say from 1 to 10 femtoseconds in that range, right? For the visible and infrared, you can check. Whereas these pulse widths, the width of the envelope of the pulse, as I said, typically varies from the shortest typically are tens of femtoseconds, and the longest you can go as long as like hundreds of picoseconds or even nanoseconds. Okay, so that's sort of the time scale. So if you go to as short as tens of femtoseconds, then you only have a few oscillation cycles here. But if you have, let's say, picosecond pulses, then you have many thousands of cycles of oscillations here. Okay. All right. So that's how we write the electric field of the pulse. Right. So the electric field, of course, goes both positive and negative. Right, because it's an oscillation. But the intensity when you take mod square is always. Okay, so then this polarization on the again right hand side will have a linear component, right? So P1. Again, these tildes are denoting rapidly varying quantities. So this is the linear part, plus we'll have a nonlinear part, the third order polarization. Okay. So first step we do similar to what we did previously, right? We take the Fourier transform and transform to the frequency domain. So okay, so we transform to frequency domain, we get, so this from Ez of t we go to Ez of omega. So now there is a spectrum, and we know that time derivatives will give me, so each time derivative will give me a factor of I omega. We can have omega square, c square. Then I have a double time derivative here also, so I'll get omega square here also. And then I'll have the linear polarization plus the nonlinear polarization. Okay, where these frequency domain quantities, so Ez omega is related to EZT by the Fourier transform, right? So right, and similarly P 1 or 3 right. So here they are functions of time. And here they are functions of frequency. Okay. So this is what we did in the beginning of the course when we derived canonical propagation equation, and then we took some particular omega that we are interested in, right? But now we have basically a bunch of omegas, right? So the spectrum of the pulse has a continuous distribution of omega. Okay, so let's just go forward from here. So it is right. So the linear polarization, right, is just the linear susceptibility times the electric field, right? So we know that the linear polarization is the linear susceptibility times the electric field by definition. Okay? So at the frequency omega, the susceptibility at frequency omega times the electric field. Okay. So we plug the linear polarization into here, right? So then, and we take that to the other side. So you know that this will give you basically the refractive index, right? Usual linear refractive index. So I get omega square by c square. Here I get 1 plus chi 1. Now on the right hand side as the source, I am left with the nonlinear polarization. Right, so this 1 plus chi we know is the dielectric constant epsilon, or which is the square of the refractive index. Right, and basically we are interested in seeing how the sort of the envelope of this pulse changes on propagation. Right, so let me rewrite. So this Ez of t was Az of t. So this is the amplitude we are interested in, times e to the I beta naught z minus omega naught t, right? So this Ez of omega, which is the Fourier transform of Ez of t, right? So for Ez of t, I can put this thing in. So Ez of omega is Az t I beta naught z minus omega naught t times e to the I omega t dt. Right? So Ez omega is a Fourier transform Ez t, and Ez t we took this form, so I put that in. So now you can see that, so this e to the I b naught z is, I can just take out of the integral, that's not dependent on time. And inside the integral, I am left with a times e to the I omega minus omega naught. Right? So you can see that's basically just the Fourier transform explicitly. So here I am left with a e to the I omega minus omega naught t dt. Right, so basically this is the Fourier transform of a at the frequency omega minus omega naught. Right, so this is basically a of z comma omega minus omega naught. So that's the Fourier transform of this a at omega minus omega. Right, so basically Ez of omega is related to a at omega minus omega naught. So omega minus omega naught is the detuning from the center frequency, right? So which we can denote with another symbol, capital omega. Okay. So this capital omega is basically omega minus omega naught, which is the detuning from center, right? So for example, when we plot the spectrum of the pulse, right, the center frequency is some omega naught, and then we are looking at these detunings away from the center frequency, right? So equivalently, so what I'm saying is, so Ez of omega, if you plot Ez of omega, that will look like this, centered at omega naught. Which is basically just a shifted version of the Fourier transform of A. So if I plot A z of omega in the detuning space, this will be centered at 0. Okay, so the Fourier transform of the envelope will give me a spectrum which is centered at 0, right? And when I multiply by the carrier, this spectrum gets shifted to omega. Okay, and basically we want to see changes for in the both in the time domain and in the spectral domain. So we want to see basically like this detuning variable capital omega is a good variable to work with, because we want to see, basically we want to center ourselves on the center frequency and see how this shape of the spectrum changes. Okay?
Sir, can you explain this graph again?
So this relation is clear?
Yes, sir.
Ez of omega is basically Az of this capital omega, which is omega minus omega.
Omega naught.
Right? So they both have the same shape, but one is just shifted by omega naught. Right? So, so when I plotted Ez of omega, that was centered at omega naught, and it had some bandwidth. Whereas this Az omega is the same shape, but it's just centered at 0, because we're looking at detunings from the center frequency. Right? So the Fourier transform of this E is basically a product. So since E is a product of this envelope times this carrier, right? So in the Fourier transform space, you can see that the Fourier transform of this guy will be the Fourier transform of this A convolved with the Fourier transform of this carrier function, which is like a delta function, right? So that just shifts the Fourier transform of A to wherever the carrier frequency is, right? So that's what it's doing. So when I multiply Az omega, or when I multiply A with this carrier, it shifts the spectrum of A from 0 to omega naught, right? Basically, we are interested in only the changes in the envelope, right? Of course, the carrier wave will still be there. So we just want to remove this carrier wave which is appearing everywhere, and we want to see only changes in the envelope, both the spectrum and time. So it's just rescaling and shifting or something, right? It's not, yeah, it's the same thing. I hope that's clear. Right, so A is the envelope of the pulse, whereas E is the whole thing. Right? So I don't know. I mean, this is nothing but this property, right? The Fourier transform of some function multiplied by some carrier e to the I omega naught t is the Fourier transform so if the Fourier transform of f of t is some f of omega. Then if I multiply f of t with some sinusoidal carrier wave here, then the Fourier transform of that thing is just the shifted version of the original. That's what I'm doing.
Okay, sir.
Okay, because we don't want to keep track of this e to the I omega naught t carrier wave everywhere. We just want to see how the envelope changes. So we're just looking at this amplitude A and its spectrum, which is basically the total electric field, except we remove the fast carrier e to the I omega naught. So that shifts the spectrum from omega naught to 0. The actual frequencies present in the pulse, of course, will be about omega naught, right? Because of course the carrier is there. But we are just interested in seeing how the so on propagation this AZ of omega will change somewhat, right? So what does that mean? That in the original pulse, my EZ of omega about omega naught is changing. Right? But it's just for ease of mathematics we're going to a change of variables. So this is a shift in the variable. Okay, maybe it will become more clear also as we go forward. But yeah, so that's okay. And similarly, for the polarization also, we can write like an envelope and a slowly varying part. So, for example, even this P3. So in the time dependent equation, we had P of t, right? So there, so P3 of z comma t, I can write as some slowly varying amplitude times a fast carrier. Okay. And then when you take the Fourier transform, again you can see that so it's the same thing which has been done here. We wrote the electric field as a slowly varying envelope times a fast carrier. Similarly, I can do with the polarization. And so in the frequency domain, the spectrum of the polarization will be the spectrum of this slowly varying envelope, which is centered at 0, right? Whereas the total polarization, which is the including the carrier, will be again shifted to omega naught. Okay, so basically we want to, I guess, transform our variables from this omega to this capital omega, because we want to see only changes in the envelope. Okay. So okay, so this, let's again go back to this equation where we were. So for Ez of omega, we can put this Az of omega times e to the IB naught z here and here. And similarly for P3 z of omega, we can put this envelope times e to the IB naught z. And then this omega by c square times n, that's just beta, right? So this is the propagation constant beta at the frequency omega. Right? So the propagation constant beta by definition is omega by c times n, right? So in a fiber or a waveguide, this will be the n effective. Right, so this is beta square, omega square by c square times n square. Okay, so we can write this equation as right. So on the left hand side, I have a double derivative with z plus beta square operating on e, which I write as a of this capital omega times e to the I b naught z, beta naught z. And then on the right hand side, for this p3 the omega also, I write the amplitude or the envelope of that polarization function times e to the I b naught z. Okay. Right, so this beta naught is basically a beta at frequency omega naught. Right, I hope that's obvious. Beta naught is beta at omega naught. Okay, so if you look at this first term, so this function has, so A is Z dependent and also this e to the I beta naught Z is also Z dependent. So we'll have to use the chain rule with this differential operator here. Okay. So if you go ahead and do that, you'll see get for first term you get is that. Okay, so this beta naught square comes when you differentiate e to the I beta naught Z twice, so you get I beta naught squared, which is beta naught squared, and then the cross terms like differentiate this ones and this ones will give you this. Right, so that's the from the first term here, and then we have a plus beta square. Right, so that's my, this is my left hand side now, and the right hand side remains that. So this e to the I beta naught Z gets cancelled on both sides. Okay. So now we are left with an equation you can see in the frequency this capital omega, which is the detuning from the center frequency, right? So that just gives me how the shape of the envelope changes. Okay, so now to proceed further, so we have beta naught here, which is the center frequency, beta naught, which is the propagation constant at the center frequency, and then we have beta at omega also here. Okay, so omega are frequencies which are closely spaced to the center frequency omega naught, right? So we can again use this Taylor expansion for beta. So beta of omega, we can expand about the center frequency to beta at omega naught plus beta 1, which is the first derivative of beta at omega naught times the dt mean omega minus omega naught plus second derivative, which is beta 2 times omega minus omega naught square, and so on. Okay, so we've done this before in the four-way mixing case, for example. Right, so beta 1 is d beta by d omega at omega naught, which is basically 1 over the group velocity right? Basically, 1 over the group velocity of this pulse. So this pulse is moving, the envelope is moving at some velocity, which is vg, right? Which is 1 over 1. Right? And then you have higher order terms starting from the GVD onwards. So typically, so what you can do is club all the higher order terms starting from the second order. So you can see this function only depends on omega minus omega naught, right? Which is basically this capital omega, right? So it's just a function of this capital omega. So this, how many ever terms you want to include starting from the second, you can club into what is called a dispersion operator d, which is a function of omega minus omega naught, or equivalently a function of this capital, right? So basically beta at omega we are writing as beta naught plus beta 1 times this capital omega tuning plus this dispersion operator, which is a function of omega. It starts with beta 2, beta 3, how many ever terms you want to keep. All that's combined in this d omega, which is called dispersion operator. Right? So what is the dispersion operator? Just right. So this dispersion operator explicitly I can write as summation from 2 to infinity, ideally, but till whatever you want to keep. Right. So the nth term is the nth order dispersion beta n, which is the nth derivative of beta with respect to omega, divided by n factorial and times this detuning omega to the nth power. Right, starting from n equal to 2 to, so that's the dispersion operator. Okay, so you can see in the equation we have a beta square here. Okay, so if we write beta like this, then beta square basically square of this, right? So it will have beta naught square. Okay, so in this expansion here, the biggest term is beta naught, right? And then this next term will be much smaller than beta naught. And then this next term will be much smaller than the previous term, right? Because it's a Taylor expansion. So higher order terms are smaller and smaller. So they're less significant. Okay, so right. So when you square this, of course, you will get 6 terms, right? Square of each term, and then the cross between each of the two. So here you'll get beta naught square plus 2 beta naught beta 1 omega plus 2 beta naught t plus beta 1 square omega square plus 2 beta 1 d. Right, plus you'll get a d square also. But we immediately neglect this d square, saying it's very small. Okay, again, as I said, this is the biggest term, then this is much smaller, then this is much even smaller. So d square would be the smallest term which we can neglect. Okay, so we neglect d square. So this is actually not exactly equal, but approximately. Okay. So now in this equation, we can plug in this for beta square. Okay. So here we have beta square and then minus beta naught square. So this beta naught square will get cancelled, right? And then we'll be left with these 4 terms: 1, 2, 3, and 4. So I explicitly write that out. So I get, so I had d square by dz square okay. Then I had this term already, 2i beta dA by dz. Right, these 2 terms are already there, and then I had minus beta naught square plus beta of omega square. Right, and for that I plug this in, and so the first term beta naught square get cancelled, and now I have 4 more terms here, which are basically these terms. Okay, and then on the right hand side I had this minus omega squared by epsilon naught c square. So omega square I write as just put it explicitly. So this was minus omega squared by epsilon naught c square. Nonlinear polarization. Right. So on the left hand side I only have this. I'm left with only this detuning variable capital omega, right? So on the right hand side I have this small omega, which is the original frequency. So I want to convert everything to this capital omega. So remember this omega is, so this capital omega is omega minus omega naught. So omega is just omega naught plus this capital omega, right? And then I take omega naught square common out here. And then I get 1 plus this capital omega by omega naught whole square inside. It will become clear in a while why I am writing it like this. But now this function is also now only in terms of this capital omega, right? Rest are all constants, omega naught c. Okay, so we are left with this equation. Right? So theta naught. Okay, so on the left hand side I have all these dispersion operators, and on the right hand side I have the nonlinear propagation. Okay, so in the monochromatic case, what we did was, so we have we took equations at each particular omega, right? But now basically we have a bunch of this. So we have a continuous band of this omega, right? So we can't actually use this equation, right? Because there are like a continuous band of omega. So we actually need to go back to the time domain. Okay, so now what we do is take an inverse Fourier transform to go back to the time domain with respect to this variable capital omega. Right? So what do I mean? So I have this a of z comma omega. So I go back to a z of t by taking the inverse Fourier transform of a z capital omega right? And then I'll have factors of omega here, and d, if you remember, had powers of this omega, right? So you know that if so if I take the derivative here, so I get this I omega out in front. This is the only time dependent term, right? So this becomes the inverse Fourier transform of I omega Az omega, right? So whenever I have a factor of omega with this Az omega, when I go back to the time domain, I get a derivative of time, right? So in general, when I take the inverse Fourier transform of the nth power of omega times a function, then I'll get the derivative n times, right? So this will be I del by del t operating n times on okay, so for each factor of omega, I get a time derivative, right, from the Fourier transform relation. So basically, wherever I have an omega, I will replace by a time derivative. Okay, so
In the inverse domain.
sorry.
So why we are taking the inverse Fourier transform of this equation?
Because we can't use this, so this is a frequency domain equation, right?
Yes, sir.
So in the monochromatic case, basically we use the frequency domain equation, right? And that's how we got the canonical propagation equation. And at particular frequencies, we wrote those equations and got some coupled amplitude equation, right? But here we have a continuous band of frequencies, right? So we don't have any specific omega here. We have a continuous spread of those, right? So if we had discrete frequencies, then we could just put omega equal to that and then use this equation, like we were doing earlier in the course. But now we have a continuous band, right? So how do we use this equation? So the only way is to integrate this over frequency, right?
Okay.
Which is basically going back into the time domain.
Okay.
So basically what we'll see is that to analyze this pulse propagation, finally it's easier to do it in the time domain rather than the frequency domain, right? So for the cases where we have monochromatic waves interacting with each other, the frequency domain equation is easier to analyze. Whereas for this pulse, actually we'll get a time domain equation, which is yeah, right? Because we can't use this equation because there's the whole spectrum of omega, right? So for each omega anyway, you have to solve and then integrate over omega, which is basically like going to the time domain. Okay, so we go back, so we take inverse Fourier transform of this equation and then go back to our time domain. So we'll keep that and then erase this. Okay, so yeah, so we inverse Fourier transform. So first term is just a derivative of z, that remains like that. So az of omega becomes az of t. Okay. Then second term here is again, so this is just a constant. 2I beta naught and then del by del z. Third term here now has omega times a z of omega. So when I take inverse Fourier transform, I get a time del by del t of az t, right? Because I have a factor of omega. Just discuss that, right? So I can write that like this. So for this omega, I'll get an iota d del by delta or del by del t of az of t. So I also have 2 beta naught here in this term also. I can combine that with this and write it like that. Okay, so this del by del t is coming because of this omega. Okay, hope that's clear. Now we go to next term. So that just so this d of course was the function of omega, right? And specifically it was the power series in omega. So when I take inverse Fourier transform, all those omegas will convert to derivative in time. right? And I can write a dispersion operator in time, d of t. Okay. So we'll see what this d of t is, but and then here also again I have 2 beta 1 then d. Now again I have omega times a, so I get a derivative in time of a. So this will be del by del t again coming from this omega.
So here there should be a convolution between the operator in the time domain and the curly by curly of t. Because we are moving to the other Fourier plane, so if one multiplies in the if one in one space it multiplies in the other domain, it gets convolved.
Well, it's a linear operator. So let's write explicitly what. So what does d do, right? So d is a power series in omega, right? So this is some beta n, some constant here, right? So when you operate d on a, right, you multiply this thing with a, right? Again, which is let's say some omega, right? So what do you get? You get, so this is going from 2 to infinity. So first term you get omega square a omega, next term will be omega cube, and so on, right? Now when you take inverse of that, this is basically derivative of time twice. This is derivative of time thrice, right? So basically, when you take go back to the time domain, it's like operating d of t on a of t, where d of t is summation of these derivatives to nth order derivatives. Okay, that clear? That's what this is.
Yes, sir.
Right, so this d of omega operating on a of omega, when I take inverse and go to time domain, it's like d of t operating on a of t. Right, where d of t I write as the summation of this nth order derivatives in that. Okay, so we got to here, and then the last term is omega square, so that's a double derivative in time. Minus beta 1 square d by dt square. Right? This all of this operates on a z of t now. Okay, so I hope it's clear how we went from now here frequency domain to time domain. So now our dispersion operator becomes a time domain operator. Again, it has the dispersion coefficient beta n, but now multiplied by nth derivative of nth order derivative with respect to time. Okay, and then what happens to the right hand side? So this, everything is a constant, except now again we have omega here, which will give me a time derivative. So this, the right hand side becomes minus omega naught by epsilon naught c square, and 1 plus I omega naught d by dt square. Now nonlinear polarization as a function of time. Okay, so I get d by dt here for this. Okay, so now I've gone to this time domain equation. Okay. And now I know what Az of t is, right? That's my pulse shape here. So I can apply this equation in the time. Of course, we'll simplify it further. It looks like a big chunk now, right? But because we know Az of t, which is basically the envelope of my pulse, I can apply this equation in the time, right? All these operators are constants and just derivatives. And then the nonlinear polarization here will be again a product of electric fields, which will basically again depend on this A, right? So specifically, what is that? You can also see what is this nonlinear polarization here. So P and L Z of t is, so basically we just have one pulse traveling through the medium, right? And it, as we discussed in the beginning of the class, it can cause self-phase modulation on itself. So we can write the nonlinear polarization. So remember, for the self-phase modulation case, we can write it like this. So mod of A square times A. So chi3 times mod of A square times A. That gives me the self-phase modulation term, right? So in the time domain, we can write the nonlinear polarization at time t is the envelope at time t mod AT square times A. So we are assuming basically instantaneous response. Right, that at each time instant, the material is responding instantaneously, and it depends only on the field amplitude at that moment, right? Which is true for most regimes, as long as, for example, you're operating far from the band gap, right? So this omega naught, the center frequency in your pulse, is much smaller than the band gap. Like, for example, in an optical fiber, which is made of silica, the band gap corresponds to a frequency in the UV range, like I don't know, 200 nanometer something. So if you're operating in the visible or infrared range, like a micron wavelength, then you're very far away from the band gap, and the response is basically instantaneous, right? Again, go back to our initial discussion of when we were discussing chi3 and frequency dependence, and when you go far away, then chi3 becomes a constant, and it's like the response function is like a delta function, instantaneous, right? So we're in that range. Okay, so now this right hand side also just is a function of A, and we have material constants. So specifically, we have the dispersion constants on the left hand side, and on the right hand side we have the nonlinearity of the material, right? And this equation will basically give you how this A Z of t transforms while propagating through this nonlinear dispersive medium. Okay, but before that, we simplify this equation a little bit more. So what do we do now is, so we go into a frame. So right now this Z and T, so this T is some absolute time, right? Like I have some external clock which I am measuring the time, and Z is basically position along the fiber or waveguide. So now we transform to a coordinate system where we are moving with the group velocity of the pulse. Okay, so basically we are interested in seeing how this envelope is changing, right? So if we move to a frame which is moving with the pulse, then it will look as if the pulse is stationary, and only we will see the local changes in the pulse shape, right? Right now we are in a frame where like we are seeing the pulse move with time, but it's more convenient to transform to a coordinate system where we are sitting, let's say, at the center of the pulse and then moving along with the pulse at the group velocity. So then we don't see the pulse moving, it's stationary, and any changes we see are changes happening in the pulse envelope. So transform to local frame of the pulse. Okay. So we define a new time coordinate tau, which is basically t minus z over vg, or equally t minus beta 1 z. Beta 1 is just inverse of vg, if you remember, right? So it's a frame which is moving at the group velocity, right? So we are moving along with the pulse, right? And then the new spatial coordinate is the same. Okay, so in this new
Sir, can you explain the mathematical expression of this transformation again?
so you can write this as so Vg of tau right. So we are defining a new coordinate system where we are shifted by how much the pulse has moved, basically, right? So we are moving with the pulse.
Z plus Vg of t, I think so. From mathematical expression.
Yeah. Vg of tau is
So Z minus Vg of tau is equal to minus of Vg of t tau.
right. So my new time coordinate. So Z is a particular location, right? And then T is some global time which is sort of, so I can fix myself at one particular Z and then see as a function of time what is happening, right? So if I'm fixed at, so let's say I'm standing at one particular Z, and then I have a clock which is counting, counting T, and then this pulse comes and so it will come and then pass me by, right? So at my location, when I measure A as a function of time, so first my pulse comes, right? Then the peak comes, then the front, then the peak, then the back, right? At a particular Z. But now what I'm saying is, I go to a frame which is moving with the pulse. Okay, so I'm only I don't see the pulse moving at all. Okay, I'm moving with the pulse, and then I have a counter which is counting time with respect to the center of the pulse. Okay, so in a sense, basically, okay, what we want to do is go from a variable of sort of two coupled, right? So here A is a function of Z and T, where actually Z and T are coupled, right? In sense like this pulse is moving with, so the Z coordinate updates with a function of time, right? So it moves forward by amount Z equal to Vg T, right? So from that we want to go to a frame where sort of the time coordinate is just the local coordinate of the pulse, and it doesn't depend, or sort of it's decoupled from the spatial location.
Okay, sir.
Okay.
Sir, isn't the equation should be Z minus of Vg of t is equal to Vg of tau? That we remain in this
Z minus.
Vg of t is equal to Vg of tau.
I mean, I guess you could equally define that. It will just be sort of flipping this tau. So your front and back of the pulse will be flipped. Okay. So if you define it like this, then basically in the tau axis also, so front of the pulse will be tau less than 0, and back of the pulse will be tau greater than 0. Right? Because so Z minus Z equal to Vgt is the center of the pulse, right? So times earlier than the center of the pulse is the front of the pulse, which means tau is less than 0, and times after the peak of the pulse is the back of the pulse, right? So go back to this picture. If I stand at a particular Z, then I measure the pulse going by, then I'll get something like this. So T small, and this center will be Z over Vg, right? Assuming, for example, the pulse is starting at Z equal to 0 and then moving with Vg, right? Then I'll get the peak at a time Z over Vg, right? So basically I'm saying that I want to center my time coordinate, so I subtract the Z of Z by Vg, right? So depending on where I am, I will get this peak at different times. right? Because the peak occurs at Z over Vg. Is that clear? So basically what I'm saying is I want to define a time axis where I subtract this Z by Vg, when now my peak always occurs at tau equal to 0 in this frame, right? So now it doesn't depend on where I am.
Okay, sir.
The pulse peak is always tau equal to 0. And then tau less than 0 is the front, tau greater than 0 is the back. Okay, it's so in the original frame, right? If you want to plot the pulse as a function of time for different positions, they look different, right? So if I change from Z1 to some Z2, and then now see as a function of time what pulse I'll measure. So this will get shifted, right, to Z2 over V. So as a function of this t-axis, where the pulse peak lies actually depends on where I am, which is sort of inconvenient, right? If I transform to this frame, so I basically subtract the spatial dependence of my arrival of the pulse, right? And now my in this local frame, doesn't matter where I am, my pulse peaks at tau equal to 0. So in my local frame, that's why it's like moving with the pulse, right? I'm at the center of the pulse and it's always peaking at tau equal to 0. Right? And now any changes that happen, so as a function of z, what can happen is that this shape changes. That's the only thing that can happen. Right? In this original case, what was happening? This pulse center was also shifting. Right? But in this new frame, the pulse center won't shift. Only only changes that can happen is shapes. On shape or extent and that kind of thing can change. Right? So then we are only measuring changes happening in the amplitude without having to keep track of how far the pulse has moved. You understand? So in the original, so at some z equal to z1, as a function of time, the pulse looks like that. Then as it propagates through the nonlinear medium, it propagates to some further distance z2. So then at z2, if I measure as a function of time, I won't get the peak at the same time, but I'll get a peak at a later time, right? And the pulse shape might have changed. Right? So if I try to be in the original coordinate frame of z and t, then I have to keep track of this also, right? That pulse has moved forward and then see if there is any change in the pulse shape. In moving to this frame, what I've done is basically get rid of this translation of the center, z over vg, right? And then see, okay, every time I'm just looking at tau equal to 0 and see as I propagate z, what is happening to the pulse.
Okay, sir. Got it.
Okay. Okay, so we basically do a coordinate transformation. So basically, we have to now transform the equation in these variables z and t into z prime and tau. Right? So how are they related? So we can just see del by del z. Right? I can use partial derivatives and write as derivative of z prime, and then derivative of z prime with z, then derivative of tau, derivative of tau with z. Okay? And now z prime z, so this is just 1. Right? So this is just the z prime. Then second term del tau by del z. Del tau by del z is minus 1 over Vg, or minus beta 1. Maybe this correct terms of beta 1. Right, so del by del z, which was my original variable, in terms of new variable, it is del by del z prime minus beta 1 del by del tau. Similarly, we can see what is del by del t. So again, I can write del by del t as del by del z prime times m by d plus del by del tau by del t. Right. Now del z prime by del t, this is 0 because z prime is only depending on z, not t. So this is 0. And then del tau by del t is just 1. Right? So del by del t is just del by del tau. Okay, so we have these transformations now. So wherever we have a del by del z, we replace by this del by del z prime minus beta 1 del by del tau. Wherever we have del by del t, we just replace by del z. Right, so we have del by del z here, del by del tau here. Okay, so we just go ahead and do that. So we have a first term here is del square by second derivative in z. Okay, so this will give me del by del z, del square by del z prime square minus 2 beta 1 del by del z prime del by del tau plus beta 1 square del square by del tau square. Right, that will be this del by del z square term, because del by del z is this, and this I have to operate twice. So I'll get del by del z prime square. I'll get beta 1 square del square by del tau square, and then I'll get the cross terms. Okay. Similarly, just go ahead. So here del by del z plus beta 1 d by dt. So d by d, del by del t is del by del tau, and d by del by del z plus beta 1 del by del tau. This is just del by del z prime. Right? From here. Okay. So we can just go ahead and do this for every term. So in the dispersion operator, remember this, we had a summation of del by del tau to del t to the n, but del by del t is just del by del tau. So this will just become t will just become tau, nothing will change. This will dispersion operator at time tau. Okay. So some terms will cancel, right? So this term will cancel with this term. So beta 1 squared del square by del tau minus beta 1 squared del square by del tau. And then we make one approximation here, is that the second derivative of z, this we neglect, saying we make the slowly varying envelope approximation, which is the same approximation we did initially when we were deriving the canonical propagation equation. Also, remember, you go back, we had a del this d square by dz square second derivative in z term, and we basically said that that is much smaller than this beta naught times single derivative term, right? And we just neglected that, which is same thing we'll do here, basically saying that the pulse envelope does not change much on a propagation length of one wavelength, right? So this is the same approximation we made. Okay, so we neglect this second derivative of z. Okay, so then the terms we are left with is okay. So these are the terms I'm left with. I've just combined some terms here, taken beta naught. So right, so combined this term, the 2i beta del by del z, with this term, beta 1 del z prime del z tau. And similarly for the dispersion terms here. So I get the same factor. Okay, and then right hand side was this, and then this P and L, where T was 3 times by 3 mod A square A. Right, so on the right hand side, I have that. Okay, so now to further simplify this, we can make another good approximation. So this term beta 1 by beta naught. Right, so beta 1 by beta naught is basically, so beta 1 is what? 1 over Vg, right? And beta naught is omega over C times the refractive index at omega naught, right? So this Vg we can write as C over Ng, which is the group index, Ng. So this is omega naught. We have omega naught by C n naught. So C's get cancelled, and you can see this is basically 1 over omega naught times Ng over n naught. Right? So n naught is the bare refractive index, or the usual phase refractive index, and Ng is the group refractive index. Right? So I don't know if you remember from your basic optics course, this Ng is related to n naught like this, right? Dn by d. Right. So typically, in most cases, this Ng and n naught are very close. They are not exactly the same, but typically they are, let's say, within 10% of each other. Okay. So it's a good approximation to say this Ng over n naught is close to 1, and basically beta 1 over beta naught is basically just 1 over omega naught. Okay, so that's the next step. So basically what we do here, beta 1 by beta naught, we replace by 1 over omega naught. Similarly here. Right, and now you can see this 1 plus I by omega naught del by del t is the same factor which is coming on the right hand side. So basically I can cancel one of these factors here, and the equation simplifies a lot. Right, and I have this 2 beta naught here common, which I can take to the other side. Okay, so I write this equation as del by del z prime of A first term so I divide the equation by 2I beta naught. Okay, so this goes away, that's why I get del by del z, right? Here I'll be left with an I. Okay, specifically a minus I, and then I take this to the other side and write it as I times D operator acting on A. Okay. And then the other term is this. So 2I beta naught divided by 2I beta naught here, right? And beta naught, again I can write omega naught C over N naught. So the term here becomes I B omega naught chi 3. No, sorry. Becomes 3 omega naught by 2C N naught. Okay, so basically we end up with this equation now with only 3 terms. So this, on the left hand side I have dA by dz, which is basically saying how my envelope changes as it propagates along z. On the right hand side there are 2 contributions to that. First one is a dispersion operator, right? So this is telling me how the pulse shape changes because of dispersion in the medium. And then the second one tells me how the pulse shape changes due to the nonlinearity, Kerr nonlinearity in the medium, which depends on mod A square, which is the intensity of. Okay, so remember we started with A was the electric field amplitude, but again it's more convenient to write it in a form where A mod A square gives me the power, right? So again we normalize A such that mod A square gives me power, right? Which is basically so take A to multiply by this constant times A effective is the effective mode area. Okay. Equivalent you can think of, I am putting a new variable A prime, which is this constant multiplied by my original amplitude A. Okay, so recall, so this factor is, so the intensity is given by this factor times mod A square, and then the power is the intensity times the effective mode area, right? So if I do this, then mod A prime square will give me power, right? So it's just a scaling. I just rewrite this equation in terms of A prime, right? So you just have this constant which gets divided here. Okay, so in terms of A prime, so we did something similar, right, when we were deriving the coupled amplitude equations in waveguides. So it's the same thing here. So in terms of A prime, it becomes Okay. And this factor here, you can check, is just gamma, the effective nonlinearity, which is omega by c into over A effective, where N2 is the nonlinear index coefficient. Okay, so this just becomes the familiar gamma, the effective nonlinearity, right? And we can drop the primes and just say that we normalize such that A mod A square is the power and Z prime was anyway Z. So you can get rid of the primes. And finally write the equation like this. So okay, so this is the final equation you get. Right, where this d of t is the dispersion operator. Right, beta n is the nth derivative of beta at omega naught. Okay, so finally we get a relatively simple equation. At least when we write it like this, of course, these operators can be complicated depending on how many orders of dispersion you want to take. Right? So this is called the nonlinear envelope equation. And basically tells you how the pulse envelope A changes on propagation through a nonlinear medium. And specifically, we can see it has contributions from dispersion in the medium and nonlinearity. Specifically, self-phase modulation.
In this equation, there should be A prime or Z prime.
Yeah, but as I said, we can just get rid of, I mean, Z, we did the change of coordinate, but Z prime was just Z, right? So we know that this is just the actual coordinate. And if we just, when we write this equation, we say that the A is normalized such that mod A square is power. So A has units of square root of what?
It was A prime, sir. A prime mod square equals to power.
Yeah, so I'm saying I've just rewritten this equation. I've got rid of the A prime and just written it as A.
Okay, sir.
Now I'm calling A as A. I mean, we initially started with some A. So now this A is of course not this A. This A is the one which is usually normalized like.
Okay, sir.
I mean, if you want to call it, you can call it B or something else. But usually in all books, etc., you will see it written it like this. That's why. Yeah, maybe I should have started with some other variable here so that it finally end up with A. Okay, so Yeah, so this has all orders of dispersion, starting from the second order, which is GVD, right? And depending on if you have a very narrow pulse or a wide bandwidth pulse, then higher order dispersion terms are important. Otherwise, mainly the contribution is from n equal to 2, which is GVD. And then here you have the self phase modulation. You've seen this term before, right? Gamma A square A. Like, for example, when we were doing forward mixing, etc. And plus there is this factor here, 1 plus I by 1 or del by del tau. This factor is called self-steepening. Okay, and it's called self-steepening because it actually leads to a steepening and asymmetry in the pulse. So what this term does is basically if you have a symmetric pulse like this, it makes it sort of asymmetric, so the front and back don't look the same, and typically usually it's the other way around. So the trailing edge of the pulse becomes steep, very steep. So that's why it's called self-steepening this stuff. Okay. So basically, this is sort of the equivalent of the canonical propagation equation that we had for monochromatic waves. This is the analogous equation for pulse. Right? Pulse is propagating through a nonlinear medium, which also has dispersion. So we'll stop here, and then next class we'll see in different parameter regimes how. So this is the full blown equation, which has all terms, right? But depending on the parameter regime, some terms can be neglected, and we'll see what happens to pulses in different sorts of regimes.